So in this video we're going to look at vector spaces, or subspaces if you want, that are generated by sets of vectors. So here's the idea. We want to take a vector space that we know, and we're going to reach into that vector space, and we can randomly grab n vectors out of that vector space. We don't even have to know what they are. They can just be n random vectors that we select from the vector space. And then once you have your n vectors, you can construct the set of all possible linear combinations of those vectors. And then we'll give that set a name. We'll call that set U. We'll let U be the set of all possible linear combinations that we can make from this randomly selected set of n vectors we've pulled out of a vector space. So we know V is a vector space. And the claim is that the set U, the set of all possible linear combinations of those n vectors, the claim is that that set U is a subspace of V. And remember, if you're a subspace, that means you're a vector space in your own right. And we say that that vector space U is spanned by or generated by the vectors that you've randomly grabbed from V, the set of vectors V sub 1 through V sub n. And notationally, we say that U is the vector space spanned by that set of vectors. So the proof of it would go like this. First, what we would do is identify that if we have grabbed n vectors from a vector space and created all possible linear combinations of those vectors and called that set of vectors U, U is a subset of V. And remember that if we have a subset of a known vector space, we just need to show closure to show that we have a subspace or a vector space in its own right. So we need to show closure under addition, and we need to show closure under scalar multiplication. Those are the two things we would need to do. So what we'll do is to show closure, we need to, under addition, we need two vectors from U, and to show closure under scalar multiplication, we need a scalar. So let's go ahead and construct those things right now. So we'll say let U and W be vectors in the set U, where U is that set of all possible linear combinations of vectors V sub 1 through V sub n, and let C be a scalar. So C is just a real number. So if U and W are in the set U, we know something. We know, I'll be really explicit, because U and W are in the set of all linear combinations of vectors V sub 1 through V sub n. That means there exist scalars K sub I, R sub I, and scalars are just real numbers, such that U and W can be written as linear combinations of V sub 1 through V sub n using those scalars. So such that the vector U is a linear combination, K sub 1 times V sub 1. U is a linear combination of the n vectors that we've pulled out of V. So K sub 1 times V sub 1 plus all the way through the nth scalar times the V sub n nth vector right there. And we know that W is also going to be a linear combination of these n vectors right here. So we're going to use R for our scalar, R sub 1 times V sub 1 plus all the way through to scalar multiple of the nth vector. So we construct the two linear combinations. And then we need to show closure under addition. So we go ahead and we add those two vectors together. U plus W, what does that look like? Well, we would do K sub 1 times V sub 1 plus R sub 1 times V sub 1. And notice we could factor the V sub 1 off. So we get K sub 1 plus R sub 1 times vector 1 plus, and we would do it for all of the n minus 1 vectors all the way up through the nth vector. And the nth vector we would get K sub n times v sub n plus r sub n times v sub n. We could factor the v sub n off using the distributive property, and we'd get k sub n plus r sub n, the sum of two scalars, times v sub n. And what we want to notice is that the sum u plus w is a linear combination of the n vectors we chose from v, because these coefficients, the k sub I plus r sub I terms, are all just scalars. A real number plus a real number is just another real number, another scalar. A real number plus a real number is just another real number, another scalar. So now we want to show also show closure under scalar multiplication. So we also can do a scalar times either the vector u or w. It won't matter. They're both arbitrary vectors from the set u. So if we do c times u, what does that look like? Well, that's going to look like u is built this way. So it's going to look like c times k sub 1 v sub 1 plus all the way through the nth vector. We'll get c times k sub n v sub n. And notice that c times u is just a linear combination of the n vectors we randomly selected from the vector space, because c times k sub 1 is just a scalar. This is the product of two real numbers, the product of two real numbers, just another scalar. So that tells us that u, the set of all possible linear combinations of these n vectors from vector space V is closed. So thus u is closed under addition and scalar multiplication. So u is a subspace of the vector space V. And remember, if you're a subspace, then you are a vector space in your own right.